Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to draw what are called impulse momentum diagrams and how to use those diagrams to write momentum equations to describe a given system. So what we're looking at here, imagine we've got this cannon sitting on the surface. This cannon is free to roll. This contact point here, imagine, can slide very easily with very little friction. In this example, we're going to assume this cannon has a mass of 1,000 kilograms, and we're going to assume it fires a cannonball, which is what I called M sub B here, at with a mass of 100 kilograms, and it can fire that ball at 900 meters per second. And what we're going to do is we're going to draw an impulse momentum diagram that describes basically the firing of the ball, and we're going to try to predict the final velocity of the cannon, which is what I'm calling VC2 here. So this series of pictures I've already drawn here. This is what I'm calling picture 1. This is an instant before the ball is fired. This 1 to 2, this is going to be where I'm going to put all my impulses acting on the system, and that's going to be happening over a very short time frame, you know, that hundredth of a second or thousandth of a second it takes to actually fire that cannonball. And here's my picture 2 here, and this is going to be an instant after the cannonball is fired. So it's not that this cannon has moved left or right any significant amount here. These are differences, or like different time frames. So when you draw an impulse momentum diagram, you typically draw the system at some state, which I've called state 1, and you draw all the momentum vectors. Now remember, momentum is mass times velocity. Since nothing is moving here, there are no momentums in picture 1. All right, the 1 to 2. This picture is for all the impulses acting on the system. Now remember, impulse is force times time. The only difference between force and impulse is the time factor. So I typically start with just a free body diagram. Here are some forces acting on the system. The cannon has a pretty significant weight. So we might draw, oops, I can draw a better force vector than that. We might put a force vector in for that. M sub G, mass of the cannon, M sub C times G. So there's for the cannon. We could include the cannonball too, the mass of the cannonball. You notice I kind of put that in here, and I'll talk about why here in a moment. But here's kind of a picture of where that cannonball would be during the firing process. The cannon is supported at the ground at these contact points here and here. So that's going to give us a normal force, or what we would typically call a normal, and that's going to be upward. Now, the cannonball is experiencing a force kind of up and right. It's being pushed by the hot expanding gases in this region. I'm going to go ahead and put that in there. Maybe I'll call it, I don't know, I'll just call it F, force on the ball. But by Newton's third law, that force that's acting on that cannonball up and right, that same force acts down and left on our cannon. Because remember Newton's third law, forces always appear in pairs. And that's pretty well it. I can't think of any other significant forces acting on this. We might be tempted to put some sort of frictional force to the right. I'm going to go ahead and leave that off. I'm going to assume this is a very low friction surface here that this can slide freely. Now, this is basically a free body of the system. These forces are forces that would typically not go in free bodies because these forces are internal to the system. I went ahead and included them because I wanted to talk a little bit about how these forces kind of relate to the entire problem here. And these are still just force vectors. This is not yet an impulse diagram. The difference between impulse and force is just the time factor. So if you take your free body and just tack delta t's on to everything, these are now impulses. Now, again, this free body or this impulse diagram is good over this very small time frame. These delta t's would be very small numbers in this example, you know, a hundredth of a second, or probably something in like thousandth of a second. These forces, like this one right here, if we call this impulse F delta t, inherently this is some average force acting on that cannonball. Same thing here. This would be kind of an average force acting on the cannon. All right. So my impulse diagram is basically done. Over here now, picture 2 is going to be for momentum vectors. So I know that the ball is moving kind of up and right. I'm going to go ahead and put a momentum vector in there for it. And that vector is going to equal mass of the ball times velocity of the ball. And this is in picture 2, so I'm going to put a 2 subscript on there to mathematically communicate that that velocity vector is in this picture. And inherently, hopefully everybody would realize that if there's no resistance, if this thing is not locked down, this cannon would tend to recoil backwards. So it now is going to have a momentum vector in this direction, which is going to equal mass of the cannon, velocity of the cannon in picture 2. So here is my picture showing all momentum vectors after the cannon is been fired, just an instant afterwards. And again, this angle between this velocity vector and the horizontal, 20 degrees. I'll go ahead and put that in there. All right, so this is how we draw impulse momentum diagrams. You draw your original momentums in picture 1. In this case, there's no vectors over here because nothing's moving. Then between 1 and 2, you draw all relevant force vectors on the system. Then you add delta t's to them to make them impulses. Now, truthfully, these two didn't really need to go into this diagram. I just wanted to put them in there to talk about their effects and why we have momentum conservations in certain directions and why we don't in this example. So again, these two in this example would actually be optional because that's an internal force to the system as long as I consider my system the cannon and the ball. These, however, this one, not optional. Those are definitely external impulses acting on the system. Then you draw your final momentum vectors. Everything in this, every vector in your second picture should be a mass times velocity. All right, now we're going to go ahead and write momentum equations. Now remember how impulse momentum works. Basically, the initial momentum of the system, I'm going to call that P. A lot of books use P to represent momentum vectors, plus any impulses acting on the system between, picture 1 and picture 2, or you could call that initial and final, it doesn't really matter. That's going to equal your new momentum, which I'm going to call P2. So when I apply that conceptually here, I'm starting with 0 momentum. Oh, I got to back up though. Remember that momentum, these are vector concepts. These are vectors, which means you apply it by direction. I'm going to go ahead and start with the x direction. Initial momentum in picture 1, x direction, calling right positive, is 0. There are no momentums in this picture. All right, plus any impulses between picture 1 and picture 2 in the x direction, because remember, this is impulses of vector concept. So I look over here and I notice, this guy here does not have a horizontal component, neither does this. And these two impulses are going to add to 0 anyway. They are internal to the system. So there is no impulse acting on this system in the x direction, as long as we define our system as the cannon and the ball together. Equals final momentum, again, only x direction. So I look at this picture now. This guy's momentum vector points kind of up and right, and you got to think in terms of components. It has a horizontal component and a vertical component. This component here is adjacent to this 20-degree angle, so its magnitude is going to be MB VB2 cosine 20 degrees. This vector component is opposite the 20-degree angle, so it's going to equal MB VB2 sine 20 degrees. So when I get back to this momentum equation for the x direction, this is the component I want for the ball. Mass of the ball, velocity ball, picture 2 times the cosine of 20 degrees. This term would be positive because this vector points right, and I'm doing right positive. The cannon, however, is also part of the system. It has a momentum to the left, mass of the cannon, velocity cannon, picture 2. No sines or cosines required. This is horizontal to this vector is parallel to the ground, so it's moving in the opposite direction of what I've defined as positive. And it doesn't need components because it's not like upper left or downer left or anything like that. So here's our momentum equation for the x direction. And I think that one actually can be solved. We're going to be able to get, I think, VC2 out of that. Before I do, however, I'm going to write out the equation for the y direction. So again, same thing, momentum concepts applied y direction. I'll go ahead and do up positive. My initial momentum y direction, 0. My impulse y direction, okay, so I look over to this picture for my impulses. I've got this impulse up, that n delta t up. And again, this is the normal force that's coming from the contact point between the wheels and the ground. We've got this guy right here, this mg delta t, and it's down, so I'm going to put minus mg delta t, and again, that mass is the mass of the cannon. We could include the cannonball, and perhaps maybe even should include the cannonball. I'm not going to. I'm just going to leave it mass of the cannon because I guess that is actually reasonably significant. You know, I'll go back and change that. I think what I'll do here is I'm going to put a T here, which is going to stand for total mass. So 1,100 kilograms here times G times delta T. This has a vertical component, but this also has a vertical component. And this guy, this impulse's vertical component is positive. This one's negative. They add to 0. Furthermore, this net impulse is 0 any way you cut it. So we don't really need to include it in this part of the picture. These are the external impulses that need to be included. These two I just put in there for discussion here, for a discussion point that's coming up in just a minute. So this represents my net impulse on the system by external forces, equals, now I look at this picture, final momentum, and again, y direction only, or the vertical direction. I got this vector component, mb vb2 sine 20 degrees, and that one is positive because that vector points up. This one does not have a vertical component, right? This momentum vector here does not have a vertical component, so I can put a plus 0 if I wanted, or I could just leave it blank. I'll go ahead and put the plus 0, indicating that I've at least considered it. So we'll go ahead and solve and get a numerical value out of this equation in a minute, but I wanted to conceptually talk about this equation here for a little bit. So here's an example where momentum is not conserved. In a lot of the physics problems you see in a typical college physics test, most of the time momentum is conserved because usually the problems that they write in textbooks usually don't have external net impulses acting on a system. This one does, however. This one has a net impulse because this term, while that cannonball is being fired, would be larger than this one. You know, if I drew that impulse picture here before it was fired, you just have the normal up, the mg down, and that's it. They would be equal. But during the firing process, what kind of happens here? We've got this impulse up and right on the ball, which creates an impulse down and left on the cannon. And this down and left on the cannon here increases that normal force. And that's why I drew these in these pictures, to have this discussion. So as a result of this, this guy ends up increasing. You can kind of imagine if this cannon were sitting on a scale, it would read some number before it's being fired, but the actual during the fire process, that scale would read a larger number. So the system does have a net impulse in the y direction, and that's why the system, which started with no momentum y direction, now has a momentum component vertical after the cannon's fired. So momentum is not conserved for this system in the y direction. Now, we could actually maybe calculate or estimate this normal. We would need to know the time frames, but I'm not going to do that for this problem. So this term right here, greater than this one, so the momentum of the system not conserved. All right, let's go ahead and get back to this horizontal equation here. So the velocity of the cannon, picture 2, if I go through and do the algebra, we'd have to add and then divide. We'd have mass of the ball, VB2 cosine 20 degrees, over the mass of the cannon. I think what I'll do here is just pause it for a moment, get a numerical value, double check it, make sure it's right, and come back and write it in. All right, I'm back here, and I got about 85 meter per second. I'm not going to bother showing the values and how they came out. I mean, suffice to say, I just took these numbers, put them in the appropriate spots, calculated a speed. Got about 85, rounded it to 2 sig figs. So This cannon would recoil with considerable speed, and it would also have a considerable kinetic energy when it recoiled. Of course, when people fire big guns like this, they tend to be locked down. In some way, shape, or form, this would normally be attached to the ground if this were a real live working cannon. And also, by the way, this was assuming, no friction at this interface here. Like this is on a wheel on a very hard surface or something. And typically, even if this were just resting on the ground without a wheel, you could get a significant impulse to the right via friction. But anyway, if this were on an extremely hard surface and very smooth where there'd be no friction interface at this surface or no friction interaction created during the firing process, recoil speed of that cannon would be around 85 meters per second. Numerical value here is not what's important. If anybody watching this video, the important parts are how to draw the impulse momentum pictures. So the initial momentums, final momentums, and the impulse between the pictures. This impulse diagram describes how and why momentums change in various directions for various parts of the system. So hope this video helps demonstrate these concepts. Have a great day.